2 minutes. Not 2 minutes, in fact, 10 minutes. Okay. What I mean by what I mean to tell you actually, the one very important concept that I want to tell you is ensemble learning. Remember that. Ensemble learning. What is that? What do you mean by ensemble learning? Actually, so far, we have discussed several algorithms. Like we started with, I think, KNN, okay, regression, classification. Then we studied Naive Bayes. Okay. Then we studied decision tree. Then we studied linear regression. Okay. Then we studied logistic regression. Okay. These are the algorithms that we have studied. But every time we implemented the model, we implemented all the model with the help of only one model only, either KNN or either Naive Bayes or decision tree or linear regression or logistic regression. There is one technique, which is basically an optimization technique known as ensemble learning, where instead of using only one machine learning algorithm, or in fact, one machine learning model, instead of using one machine learning model, you will use collection of machine learning models. Collection of machine learning model means in ensemble learning, we will be using more than one machine learning model to predict my output. More than one machine learning model we will be using to do the prediction of the output. And how? Understand why it has been basically evolved. Actually, there are two kind of problems as we have studied. One is underfitting. Sorry. Underfitting. And second one is overfitting. These two are big problems. What is underfitting? When your model is not performing, not able to guess the pattern or not able to follow the pattern of the data. Okay. Not able to capture pattern among the data. Okay. Not able to capture pattern among the data. That means in this case, it is not performing good on the training data, not performing good on the testing data. Poorly it is performing. Okay. And that's why your performance matrix or accuracy is coming very bad. That is nothing but underfit. Okay. Your model is not able to fit the data, performing very bad accuracy, training and everything. In overfitting case, what happens? The model is fitted very well. It is overlearned everything, overlearned from training data. Overlearned from training data. Overlearned means very good performance on the training data. Okay, very good performance on the training data, good performance on training data, but not good performance on test data. These are the two common problems. One is underfitting, means neither performance good on training nor testing. In overfitting, performance is good on training, but not on testing. Okay. So what we say, whenever model is underfitting, okay, we will say that we will have poor accuracy or a poor matrix, whatever we are calling that, poor accuracy or poor performance, rather we can say that, on both the things. And such underfitting case is known as that my model has a high bias. My model has a high bias. Okay. Second case is overfitting. Okay. Means good performance on the training data, but bad performance on the test data. Then we call it as my model has high variance. Okay. So whenever your model will learn more than required or very much from the training data, means it mug up everything from the training data, then all that model will be having high variance. And even if it is not able to predict the trend, then it has a high bias. So in both cases, objective is different. If you're having overfitting, that is a very common scenario. Then you want to reduce the variance, and to reduce the variance, you need algorithms known as bagging algorithms. Bagging algorithms or bagging techniques rather. And to increase the accuracy We need boosting to increase the performance. We need boosting. So these are known as boosting techniques. Okay, so to deal with these problems, these are interview questions. How you can deal with the underfittings? You will say that underfitting can be dealt with the boosting techniques. How can I deal with the overfitting? Sir, overfitting can be dealt with the, one of the technique is bagging techniques. Okay, bagging techniques. One is boosting techniques, one is bagging techniques. And what is bagging techniques? Let me come to that. Okay, let me come to that. For this purpose, underfitting and overfitting, this ensemble learning has been designed. Ensemble learning has been designed. Ensemble learning has been designed in which we will be using more than one machine learning model. More than one machine learning model. Okay. So as I tell you, these are two types. One is bagging. Second one is boosting. And remember, both will have multiple machine learning models together. Instead of doing prediction from one, we will do prediction from multiple. How? I'll tell you. In bagging, you will have multiple machine learning model like this. First of all, bagging stands for bootstrap aggregation. Aggregation. Okay. Short form known as bagging. In detail, it is known as bootstrap aggregation. In detail, it is known as bootstrap aggregation. Okay. Understand what do you mean by that? What I am going to do, I will take some machine learning models like ML 1, 2, 3. Suppose I am taking one machine learning model as a decision tree, second decision tree, third decision tree. In earlier cases, we always took only one algorithm. That is only one in doing prediction, train that model and doing prediction from that. Okay. So suppose I took 3 or 4, whatever you will specify. You will take that much machine learning models. Example, decision tree, decision tree, decision tree, all will be same. So decision tree, decision tree, decision tree, decision tree. You took that one. Okay. Now what you will do, out of your, suppose you have 1000 training points. This will be known as your population. You have 1000 points. This will be known as your population. So out of those 1000 points, you will take some random samples. You will take some random samples, and on those random samples, you will train your first model, known as, suppose, model 1. You will train your first model known as model 1. Then you will put these samples back. Okay, it means replacement. Now you will again choose some random samples. You will again choose some random samples. Means these samples are coming after replacement, right? We put it back, then we are taking again. Okay, put it back and then taking again. So again taking some random samples, and we will train second model on that random samples. This is model 2. Again, with the replacement, we will again take some random samples and train our machine learning model 3rd. Example, you can have many more. Got an idea? What is bootstrapping? This is bootstrapping. From your population, picking random samples with replacement. Okay, so we will, entire population, we will pick some random samples, train this model. Again, same, this all thing will happen in parallel. Remember, this all thing is going to happen in parallel. Some random samples taken, trained. At the same time, replacement, some random samples taken, trained. Again, some random samples taken, trained. All things will happen in parallel. Okay, at the same time they will happen. Now, suppose you want to do classification. You will want to do classification. Okay, so what you are going to do, you will pass your test data. You will pass data to all 3 algorithms. To this, to this, to this, all the test data. You will say, okay, what it is saying, what it is saying, what it is saying, what it is saying means which class it is predicting, which class it is predicting, which class it is predicting. Okay, then you will do maximum voting. Okay, among these three, which is showing majority in class of something. It's very much like you, when you want to purchase a car, you talk to 1000 people. You talk to 1,000 people. Okay, your 5 to 6 friends, and your 5 friends are saying, okay, you should buy Maruti, and your one friend is saying, buy Volkswagen. Which car will you purchase? Of course, the maximum one. You are receiving response for maximum one. Okay, so same way. So if we are building a classification, so suppose it is predicting class 1, it is predicting class 2, but this is also predicting class 1. So maximum votes are in which favor? Class 1. So you will say it is class. This is nothing but your bagging, and very common bagging algorithm is your random forest. A very common bagging algorithm is your random forest algorithm. Very common bagging algorithm is a random forest algorithm. And you can see why random forest, because it consists of which machine learning model random forest uses is always uses decision tree. It uses decision tree. And in ensemble learning, we will have various models, right? Various model 1, 2, 3. So suppose I'm having 100 models, and in fact, we can say we can have 100 decision trees. So if we connect several trees are there in a place, several trees are there. So which place have several trees? Remember, a forest have several trees. A forest has several trees. That's why the name has been given, random forest. Understand from the forest. Forest consists of what? Several trees. So which algorithm it is going to use? Decision trees, several decision trees. And why random name is being given? From the topic bootstrapping. You must have an idea now. Please tell me, is it fine, everyone? It's a very, very famous algorithm. Please tell me.
Yes, sir.
Is it okay? So
yes, sir.
Basically what it does, it prevents your overfitting. It prevents your overfitting. Okay, because you are not predicting on the basis of one, you are taking multiple help. So somebody will help you out at least. Somebody is going to help you out. Our objective was to what? Bagging case. Reduce overfitting. Don't overfit on the trained data. But now you are asking for multiple people. So chances of that is very much less. Is it fine, everyone? Yeah. And suppose instead of classification, if you are doing regression, then what you will do, you will not do maximum voting. You will say, okay, example, it is giving 4.2, it is giving 5.1, it is giving 4.9. So you will take mean of these three. You will take mean of 4.2 plus 5.1 plus 4.9, and mean is 1, 2, and 3 divided by 3. So this will be a final output in case of regression. Because regression have continuous output, you will have some output, you will take average or mean of those. That will be your final regression output. So you will have a random forest classifier or bootstrap classifier, bootstrap regressor as well. Is it okay, everyone? How you can deal with the overfitting problem with the help of bagging techniques? Is it fine?
Yes.
Okay. And if somebody asks you what is a random forest, you can say it's a bagging technique which is used to reduce our high variance or overfitting. And why it is called random forest? It is based on bootstrap aggregation, and as a estimator, as a machine learning model, it uses decision tree. That's why the name random forest has been given. Very popular algorithm. Similarly, in boosting, again, multiple algorithms will be used. But remember, here all algorithms are trained in parallel. But boosting is used what? Boosting is used to boost the accuracy or performance. Its objective is different now. Boost the performance. Boost the performance. Come out of the underfitting. So what it does? See, entire training data will be taken. Entire training data will be taken, and one machine learning model will be trained on this. Entire training data, we were not taking entire training data, right? We were picking random samples. Random samples we were taking and training one model on the basis of that, right? Here, what is happening? We will take entire training data. So every machine learning model is going to get trained on the same data, but thing will different. Now, what will happen? It will give some performance. So some predictions will be right. Some predictions will be wrong, right? If this model is doing something, so some predictions will be accurate, some predictions will be wrong. So it will identify, okay, these input corresponding, suppose I have an input variable x1, x2, x3, and y. Okay, suppose this is 1, 1, 0, it is giving 1, it is correct prediction. This is 1, 0, 1. Okay. And this data point, it is giving, it should be 0, but unfortunately it is predicting 1. So it will identify that. Okay. This is giving wrong result. This is giving this for this data point, it is giving wrong result. Okay. For this data point, it is giving wrong result. Okay. Similarly, for other, suppose it is giving right result 10110, it is giving correct result, fine. So what happens in this case? We will have multiple machine learning models now, but those machine learning models will work sequentially. This machine learning model will try to rectify mistakes done by previous machine learning model. This machine learning model will try to rectify the mistakes of previous machine learning model. How it does? Those data points which are here, which are giving wrong classifications, those will be assigned higher weights. Some weights will be assigned to everything. So as we assign higher weights to them, example, for this data point, weight is 1 or 10. For the correct one, we will have a less weight. For example, it is for is only the weight is 1. But all for the wrong data points, it will have more weights. So that more weightage is given to these points, because these points, this algorithm was not able to correctly classify. So when we are passing it to the second model, its weight will have a higher weightage. Its weight will have a higher weightage, so that this machine learning model tries to rectify that mistake, which has been done by the previous one. So now again, second machine learning model will make some mistakes. Again, it will try to rectify. Of course, performance will be improved somehow from this to this. Somehow it will be improved, but it will do some mistakes. So again, when data points will be passed to the next one, the data points will be passed to the next one, means same inputs will be coming here. Same input, exactly same inputs. Okay, so this is inputs coming to first one. Same input will come to the second model, but how it will come? By assigning some weights. Assigning some weights. Here, first of all, we give directly. So those inputs for which first model is giving the wrong output, those will be assigned higher weights. Suppose this for particular input, whatever input is there, it will tell, okay, this is the corresponding wrong. So please assign some higher weight. So when higher weight is assigned, so it will try to rectify that mistake. Again, whatever mistakes it will do, those mistakes will be tried to rectified by third model. So they will work in sequence. First, this will evaluate. And it will tell, okay, for these data points, I'm doing mistake. You try to rectify. It will try to rectify them. Again, whatever mistakes it is doing, this machine learning model will try to rectify. Whatever mistakes it is trying to doing, this machine learning model will try to rectify. So everything work in sequence. All receive same inputs, same input, exactly same input. In previous case, randomly inputs were given to different samples. Here it will not be the case. Here same inputs will be given, but condition that when we move from the first stage to second stage, those inputs will be weighted. And how weighted, I just told you. For those data points which have a wrong inputs, a higher weights will be assigned, right? So that you can concentrate on removing this error. This is nothing but your boosting algorithms. Okay, so biggest difference in bagging, all algorithms evaluate simultaneously, get trained simultaneously. Here they get trained sequentially because they try to rectify the mistake of previous algorithm. Is it fine, everyone? So this is you can say series structure. Earlier one was a parallel structure. Because the objective is clear. We want to increase the performance. So whatever mistake he is doing, rectify it. Second is doing, rectify third. I hope it is okay, everyone. Is it fine?
Yes, sir.
Others, please, if you are listening, please at least confirm. Is it fine, everyone?
Yes, sir.
Okay, clear? So remember, these are your ensemble techniques, which uses multiple machine learning models at the same time. When all the algorithms or machine learning models are getting trained simultaneously, that will be a random forest. And when they will be trained sequentially, so that one machine learning model will try to rectify mistakes done by the previous model, that will be boosting technique. Objective is different altogether. There, Problem was that it was overfitting. So we can train simultaneously, but take opinion of everyone. Tell me, you tell me. Whichever giving the maximum voting, we choose that. Here, we're trying to rectify the mistake done by the previous, because here our model is not overfitting. It is not even performing well. We're trying to improve the performance. So every model tries to improve the performance of previous machine learning model. So it will try to improve the performance of this one. It will try to improve the performance of this one. And for example, bagging, I just told you, example of bagging classifier is there is a separate bagging classifier as in fact, I'll just show you in 2 minutes. And in fact, there is one very common, very famous algorithm known as random forest. And similarly for boosting, there are several. For example, you have a ADA boost or adaptive boosting. You will see that. Okay. Similarly, you have gradient boosting algorithms. Okay. These are examples of boosting, and how easy this is. Every one of us know how to do the basic formatting, but how we are using them, let me show you just that thing. I'm just creating new Python 3 file. Okay. So what I'm saying, see, import pandas SPD. Okay. Now I will type to use a bagging algorithm. See, from sklearn dot ensemble, sklearn dot ensemble. See, it came, entered. Let me zoom it. I think it is minimized somehow. Yeah, sklearn dot ensemble import. What happened here? What just happened? Okay, import bagging automatically should come. Both the things are say bagging classifier, bagging regressor. So both options are there. This is first option. Okay, same way. So class has been imported. We can create an instance of this. How? Model equal to bagging classifier. And here there will be term known as estimator. If we go inside and type, let me go shift and tab. See, can you see there's an option known as base estimator, and also an option known as n estimators, means how many machine learning models you want. For example, we took 3. It is taking by default 10. You can specify 100, 200, 300, how many samples you want. And what base estimator you want, which machine learning model you want to use. Suppose I want to use any machine learning model. Suppose I am saying that from sklearn dot base, sorry, sklearn dot naive base import Gaussian NB, means we are using naive base classifier. I'm just giving an example. You can use anyone, Gaussian NB. Okay. You create an instance of that. I'm saying estimator, base estimator is equal to instance of that. Gaussian NB. Okay. So this becomes my base estimator. Not necessarily you want to use Gaussian NB. Any model you can use KNN. Okay. So you have to just import that. Let me show you all the examples. You will get an idea from sklearn. Dot nebus import a nebus classifier. Okay, and I create an instance of that. Suppose base 2. Okay. Nebus, why it is not taking? Nebus, take it. I think if we haven't executed this, so execute it, now it will take. Yeah, a nebus classifier. Okay, I took it. Now here, you can tell which machine learning model you want to use as a estimator. Any machine learning algorithm you want to use. Suppose it is a term known as base estimator. You will use here, and you will specify here which machine learning algorithm you want to use. For example, I may write base. Base means which algorithm it is going to work? Gaussian NB, a naive-based classifier. If I mention here base 2, then which algorithm it is going to use? A Nebus classifier. Similarly, decision tree you may use. Any algorithm you may use here. Okay, and you have to tell them how many models of the same base estimator you want. For example, I'm saying Gaussian NB. Then how many machine learning models of you want? So you will specify by this n estimators. Okay, n estimators. By default, it is taking 10. You may specify 20. Means 20 machine learning algorithm at the same time I want to train. I hope you get an idea now. Is it fine, everyone?
Yes, sir.
Okay, so your bagging classifier can work on which machine learning model? You say any machine learning model. Any machine learning model can be passed as a base estimator. So start working on that as that easy, right? After creating an instance, you know what to do. You know, very easy. Model dot fit, same process. When which X train and X test, that you can do easily. I hope you don't have any problem in that. Is it fine, everyone? Please tell me. Is it okay?
Yes. Yes, sir.
Similarly, you can use regressor as well. Both options were there. So classifier, regressor. Now, same way, there is one more algorithm, as I told you, from sklearn. 1 second, your bagging classifier is known as sklearn dot ensemble import random forest classifier, random forest regressor, right? But you know, in that case, you don't have to specify base estimator because it's a forest classifier. So which is the base estimator for this? Tell me. I just explained you. Which one will be for this? It's a forest. In forest, what is the available thing? In forest, what is the maximum thing which is available in the forest? Several
decision tree.
Yes, several decision trees. So it will have several decision trees inside. Several decision trees inside. So you don't have to specify that one inside this. So if I check it, there was an option of base estimator. Here it won't have. Suppose model 1 I'm mentioning as random forest classifier. If I go inside, and if you can check, there is no option of base estimator. Okay? There is no option of base estimator. And by default, it is showing Gini impurity, remember? And this Gini impurity was in decision tree only. We can specify estimators, means how many models you want. That is available, right? But which machine learning model you want to inside, it is not available because by default, it uses decision tree only. By default, it uses decision tree, but thing is that you have to specify one parameter in this for sure, random state. Otherwise, what will happen? It will work for sure if you don't specify. Otherwise, you are learning same algorithm second time, it is going to give different result. For that purpose, we specify this. Okay? So we get an idea how strong and how powerful is your bagging classifiers. This is, I think, rather than using random forest is good. I don't doubt with that. But bagging classifier gives me the power to use any machine learning algorithm as a base estimator. This is the biggest power of bagging classifier. Okay. Similarly, let's move now. Next thing. From sklearn, this time again to ensemble. Okay. Import. See, I'm just pressing A and pressing tab. I have AdaBoost classifier and AdaBoost regressor. These are your boosting algorithms, not bagging. Boosting means they try to improve your performance. They try to minimize your bias. They try to increase your accuracy. You can use classifier and regressor both. And it will also ask you, see, if I create model 2 is equal to AdaBoost classifier, it will also have an option of, see, base estimator. So here also, you can specify which machine learning algorithm you want to use. Any machine learning algorithm. But remember, if it is a classifier and if you pass here linear regression, then you are fool. You are doing mistake. Linear regression is for regression purpose only. So you have to put a classifier only. Okay, like KNN or naive Bayes or logistic regression or decision tree. Okay, same way, very much like this, you can pass this as well. And here also you have estimators. How many estimators means how many machine learning models you want. It is there. An estimator rate. And even if there is the option of learning rate as well. Right? So you can specify here very much like this. Your RadaBoost classifier. Which algorithm you want to use. Base estimator means base 2. This is our base 2. Base 2 is what? K-NIBUS classifier. You want to use Gaussian NB? Okay, make it base only. Anything you can specify. Anything. Whichever machine learning model you want to use, just first create an instance of that and use it. Or you can directly create an instance here as well, directly. It's entirely your choice. Okay, this is how much powerful. And there is one more classifier of your boosting category, gradient boosting, very popular. sklearn.ensemble, import. And after this, you know everything what to do. Once you create an instance, just model.fit on training data. And any algorithm, very much like this. And once it is fitted, we can predict the data from that. That's what I'm not explaining it. It will take time. So you can understand the concept because we have done fitting and prediction several times. Several times we have done this prediction and fitting. Okay. That's why I'm not doing. So models on import, and there is a gradient boosting. Classifier and gradient boosting regressive. It also uses a decision tree. Let me show you that. And let me click it. And if you go here and create model 3 equals to gradient boosting classifier. If I go inside, see, it is also not asking me. It is also not asking me base estimator. It is asking me number of estimators, but it is not asking me base estimator because by default it uses your decision tree in Java. Okay, very much like random forest uses decision tree for bagging purpose. It uses your decision tree for boosting purpose. Okay, so anything can be used, entirely your choice. So we get an idea what is ensemble learning. Instead of using only one machine learning model, more than one machine learning model will be improved. When we want those machine learning model will be trained simultaneously, that will be your bagging concept, which will try to reduce your variance, right? Or reduce the overfitting. And when those will work in sequentially, means one machine learning model will try to rectify the mistakes done by the previous one. That will be your boosting technique, which will try to minimize your bias or try to improve your performance or try to reduce underfitting. So for removing your overfitting, we will go for bagging purpose. And when we are trying to reduce our underfitting, we'll go with the boosting. Now, one very common question. Bias is good or high bias is good or high variance is good? Which is good? What do you say? Which is good? Which one is good thing? High bias or high variance? Bias, you get an idea, na, underfitting. Variance, you got an idea, overfitting. Which is good? Underfitting or overfitting?
Overfitting, sir.
Both are bad, actually. Both are bad.
Okay.
To do, both are bad. Both are not. If you're performing good on training data, right, and not performing good on the test data, then your model is third class for us, right or wrong? It's useless. Because if you are not able to perform in the real-time scenario, then your model is useless. Both are not good. Both are not good. So if we try to reduce the bias, how can we reduce the bias? Okay, by making our model complex. But problem is that we will then try to move towards the variance side. If we try to make our model complex, then overfitting will come. If we try to make our model simple, underfitting will come. So what is the issue? So we have to make a trade-off between bias and variance. Okay, we have to make a trade-off between bias and variance. Our optimum point should be chosen for bias and variance. Both are not good for us. So we have to make a compromise between bias and variance, and this is known as bias-variance trade-off. I hope you get an idea, right? To reduce the bias, we have to make our model a bit complex. But if we are trying to make our model complex, it will overfit. Both are like contradictions. So what we have to do, we don't have to make our model very complex, otherwise it will overfit. We don't want to make our model very simple, otherwise it is underfit. So what need to do? Choose an optimum thing. Choose the optimum thing. This is nothing but your bias variance trade-off. Okay, a very common question. What is bias variance trade-off? I hope you get an idea, everyone.
Sir, one thing I would like to say,
जी, जी.
सर जो हम जैसे कहते हैं मॉडल इज इक्वल टू बैगिंग क्लासिफायर,
Yes, sir.
तो इसमें वो बता रहा है नेम बैगिंग क्लासिफायर इज नॉट डिफाइंड,
Sir,
जबकि इससे पहले वाला
did you use this ensemble?
यस ये इससे पहले के सब चल रहा
Yes.
है फ्रॉम sklearn डॉट ensemble import बैगिंग क्लास, इट इज वर्किंग परफेक्टली,
It
बट
executed.
मॉडल बैगिंग क्लासिफायर में मना कर रहा है.
Sir, no, actually issue is that just check your bagging classifier spelling.
Spelling is
Just copy and paste from.
BAGGING.
Just copy and paste from above. It will run for sure. Just copy and paste from above.
I'm trying.
And put
Sir,
a. Actually, whenever we create an instance, remember, are you putting bracket or not? That is very important. It is a class, right? So we are creating object of this. Whenever you are creating object, don't forget to put bracket. Don't forget to put bracket. See, are you doing this? Please check this. So did it run? Please check.
Well done, Mr. Wilson. He's also had a wonderful victory, I must.
Is it fine, sir? Sir is there or not? I don't know. Rakesh, sir, are you there? No, he's not there, I guess. He was asking, but he's not here. Okay, fine. So, somebody is trying to speak something, but I'm not able to hear. Rakesh, sir, your voice is not coming properly. Is anybody able to hear him? What is he saying? Is anybody able to hear what sir is saying?
No, sir.
Sir, you're okay, working now. Fine, fine. Okay, great. Okay. So I'm moving now to a project. Okay, we'll see the complete flow of that project. So let me open a project, and I intentionally taken a data set which you have worked on. Okay, so that you can get an idea also. Titanic is where? Yeah. But this time I've taken a complete data set. Earlier I got a data set which was having few things missing. This time data set is complete. So see properly everything, please. See everything properly, how it will work. Okay. So before starting a project, a data set will be given to you. Understand each and everything. A data set will be given to you, and sit with your client and take your time and sit with your client. Just a second. Why it is not working? What happened? Okay, this is removed. Okay. So sit with your client, ask for his requirement. Okay, sir, which parameter is important for you? Which parameter is not important for you? Discuss with him. Spend time with him. That is very much important. This is known as data validation process. Talk with him. Okay, sir, this is the data set which has been received from your end. So these things are required, means which of the parameters you think is very important, you want to include in your machine learning model and everything. Okay, so you discuss with them. Once that is ready, note it down somewhere and then move. So suppose after all this discussion, I got a data set. After that, I'll import some required libraries. So what I have done, imported some libraries like Pandas SPD, NumPy as NP, Matplotlib.pyplot as PLT, Seaborn as SNS, and so that I should not receive any warnings. Otherwise, red lines come over there. If you have seen, I've imported warnings from there. So I import warnings, and after importing warnings, I just use warning.filter warnings ignore. Okay. So what it will not allow any warning to appear in my window right now. So no warning will be coming here. Those warnings which we saw in the past time, all the warnings will be ignored. So I just have to import all the necessary libraries which are required and run them. Okay. This has been done. After importing all the libraries, I will read my data. I will try to read my data. Okay. So this is a CSV file, titaniccomp.csv, complete file it is. That's why I'm saying titaniccomplete.csv. I just read that and save the data into a data frame using the pandas. So I just run that. Okay. I'm able to read data in that. Let me have a picture of the data set, what kind of data it is. So I move to third row and try to see first 5 rows of the data set. Okay. So this is my data set, which is available. And if I remember correctly, in earlier data set that we had, we didn't have this ticket column. We didn't have this cabin column, and we didn't have this embarked column. These 3 columns were missing that time. Okay. So in this complete data set, all these 3 things are available. Ticket is there, cabin is there, and embarked is there. This is complete data set. So I saw that. And at the beginning time only, I asked my client, okay, sir, what is your requirement? So he said that, okay, I just want to know from my data set, depending on the parameters, whether the person will survive or not. So immediately everything come to my mind. Okay, this is my output variable or the dependent variable, and rest of the parameters are my input variables or independent parameters. These are my independent parameters, and this is my dependent parameter. Perfect. And immediately I should analyze everything. Okay, this is passenger ID, which is unique to everyone. So I will not need that. I keep it in mind. Okay. These names are unique for everyone. Okay. This will again not make any sense for me. This ticket again will not make any sense for me. Rest, let me put it there. Okay. So 3 columns, I'm 100% sure I will not be needing in my machine learning model, because that doesn't make any sense. All are unique here and all are unique here. So these are not required, and they will not make any sense in predicting my machine learning model. I keep that in mind, and I'm going to drop that very soon. Then I moved here and check the shape of the data. How many rows are there and how many columns are there, so that I get a clear picture of the data. So, okay, in fall, there are 891 rows are there and 12 columns are there. Out of those 12 columns, 1 column is my dependent variable or output variable, and rest are my input variable. Perfect. Now let me check it out. Although I can, from this data set only, I can come to know which are my numeric column and which are my non-numeric column. The non-numeric column, pandas recognize as a object. Okay. So let me check the info of that data types. So I come across perfectly my name, as it is a text, it's an object. Sex is a gender, which is an object. Ticket is an object. Cabin is an object. Embarked is an object. Now understand, let me see one by one. Passenger ID is the ID assigned to everyone. Let's come here. You have to see everything and systematically understand what every column means. Survive means person will survive or not. T class means passenger class, in which class the passenger was traveling. Name is clear to everyone. Sex is clear. Age is clear. This is siblings. Okay, this is siblings and everyone, which is noted. This is parents and children's. Parents, PARC, it is parents and children's. Ticket is clear. Fare is clear. Cabin number is clear. Embark means where from they have done the boarding from. So there are different options, S, C, S, different options are there. So this means embark means from where they have boarded the Titanic ship. This is embark. So understanding each and every column is very important. In this case, we are having only 4, 5, 6, 7, 8, just so 12 parameters. I remember very well, barely 17 or 18 days ago, I worked on a machine learning project, and it is still working on. My work has been done. Now somebody else is working on their part. It had 130 columns. Okay? It had 130 columns. So depends on the industry scenario, you may get a different projects. And depending upon that, even your EDA will take 7 days, 8 days. Only building machine learning model is a 5 minutes time. You know that. More than that. Basic work is EDA and data pre-processing. So we are going to do everything today. Okay. So I moved ahead. I checked it out further. Now let me check some statistics. Okay. Statistical summary of all the numeric columns, which are numeric columns, which we can see here. So I'm just using df.describe, which will give me statistical summary of the numeric column. So just click. So see all the columns which were numeric are appearing here. Passenger ID, survived, passenger class, age, sibling, parent, children, and fare. Those columns which were categorical or object, these are not showing here because they doesn't have a statistical summary like this one, standard deviation, min, max. So this will give me some data. For example, count is there are 891 rows in every. See, in age, we can see in everything we have 891 rows. Okay. But age has only 714 rows. Immediate thing, something come to my mind. Immediately, something come to my mind. There are only 740 rows. That means there should be 100% missing values. Otherwise, everyone else is having 891. Okay, you can check it out. But this one is having 714. I'm talking about numerical columns. We'll come to our categorical columns as well. Okay. Then we try to find out what is the maximum value, what is the minimum value, so that we can go through that. What is the standard deviation? What is min value, max value? Everything we can see from here. After that, we try to find the correlation, because if two columns are highly correlated, okay, that means they are very much related. They are conveying the same information. So it's not good to have multiple columns of which are conveying the same information. Otherwise, same problem, your model is going to become complex, and in later stage is going to be overfit. So we have to avoid that. We have to check, is there any high correlation among the columns? So we will use df.cor. So it will give me correlation among the numeric columns. All the numeric columns, whatever correlation is there, it will show me. So let me run this. Now we can check one by one. This is all the numeric columns which are appearing here, and same are appearing here. So passenger and passenger, both are same columns. Of course, my correlation will be 1. Somewhere I have a negative correlation, somewhere I have a positive correlation. You get an idea what is negative. If one is increasing, other is decreasing, you will have a negative correlation. And when both are, one is increasing, other is also increasing, you will have a positive correlation. The thing is that check it. Are you having correlation higher, 0.9 or 0.9 above, something like that? So let me check. With passenger, in other column, there is no high correlation. Perfect. With the survived, let me check. There is no high correlation. Okay. Passenger class, there is not very much high correlation. They're not very much high. Okay, correlation is there significant. See, if we see passenger class and fare, this is significant correlation, but negative. But negative correlation. Okay, as obvious, passenger class 1 is class 1 passengers, right? Class 1 passenger, they will have a high fare, right? They will have a high fare. Passenger class 3, although their numeric weightage is 3, class 1, class 2, class 3, but passenger class 3 is a lower class. They will have a lower fare. So of course, we'll have a negative correlation. I hope you can relate the thing. The person who are traveling in general tends to pay less. Okay. And the person who are traveling in the class 1, they have to pay a lot higher. So numerical weightage, class 1 is only 1, 2, and 3 this way, right? But class 1 is paying higher fare. Class 3 is paying lower fare. So negative correlation is expected. And you have to understand your data first of all, okay? And this comes with the domain knowledge. That's why if you are new to your company, discuss with them, learn their business. What is happening there, okay? Now I'm going to the age. Not very significant correlation I can see anywhere, okay? And with sibling, not very significant, but somehow positive is there, okay? As parents and children, not very, very high, but some positive correlation is there. And fare, if we want to see, not significant, okay? But there should be something fare and passenger class. So same correlation is being visible here. You can see 0.4950. And if we go here with the passenger class and see fare, same correlation is available here. So we have understood our data. So in this data, correlation wise, we need not remove any column. Let them stay because none is having 0.9 or above, minus 0.9 or above. Okay. Let us check now missing values. Okay. Let us check now missing values in the data. So I'm going there. So as I was expecting, each column has 177 missing values. Each column has 177 missing values. Perfectly clear. I was expecting, I got an idea here looking at here only. Where? When we checked something in this column. Here the count was 740 in each column and others were having 891. Immediately I got an idea there should be some missing values. And same is being communicated by this data. Age is having missing value. But in that case, only numeric columns were available. But when we are checking through df.isnal.sum, I can see even cabin has 687 missing values. Okay, 687 missing values. Can you see that? Okay. And embarked has 2 missing values. Not very high, only 2 missing values. Is it fine, everyone?
Yes, sir.
Okay, perfect. See properly. Workflow is very important. Please see and tell me.
Yes, sir.
Okay, perfect. So moving ahead, let me see these missing value with the help of heat map, and you will get much more clear picture. This way, although we can say out of 891, 687 is missing value. So what data we are having? Okay, what data we are having? Already 687 rows are gone. So almost no information it is going to come in way. Very little data it is providing. Okay, and same thing should be conversed by heat map. In the heat map, we just pass df.isNull. So we can get a pictorial representation of the missing values. Okay, I got an idea. Can you see? These are missing values in case of each column, but see the cabin column, almost white, 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 white everywhere. So this column is having almost no information. Should I keep this column? Normally missing values are treated two ways. Either drop them or impute them by the significant, whatever is required. Okay, it is a categorical column, so ideally we should substitute by more. But see, almost none data is here. More than 70% data is absent here. So why we are keeping this column even, right? So what is a good idea? Instead of keeping it, drop this column. So I decided, okay, I'll drop the cabin column. I will drop the cabin column. I said df.drop cabin, x is equal to 1 and in place is equal to true. This way, my cabin column will be dropped. So I run this. Okay, my column has been dropped, and let me confirm. Okay, I don't have the cabin column further. Okay, and I can confirm same thing with the heat map again. See, now see this here. Here we were having a white continuous column available in the previous diagram. This has gone because here it was cabin. Now it has gone from. Is it fine, everyone? Please tell me.
Yes, sir.
Okay, so now what I'm going to do, as the beginning, I decided that I will not be using passenger ID. It is communicating unique information. I will not be using name. It is communicating unique information. Ticket, I will not be using. So I'm going to drop all 3 columns, passenger ID, name, and ticket. They are not of my use. So I'm going again. I'm saying df.drop. In the list I pass because I have to use multiple column at the same time. That's why I use the list here. If I am using only 1 column to drop, see, I don't have to pass the list. Just directly I can use it. But when I'm passing multiple columns, then you should use a list icon. So I just use list icon. Okay, and x is equal to 1, in place equal to true. Perfect. I use that and run it. And now let us check head. Now all the columns which were required have gone now. Is it fine, everyone? Is it okay?
Right, sir.
Okay, okay. So now what you should do? Okay, I've understood everything. Before converting these to numeric columns, let us do some analysis. There are 2 kinds of analysis you will be doing: univariate and bivariate. Univariate means you will analyze each parameter one by one. Okay, and try to see what is the trend in the data. You will try to see what is the trend in the data. Univariate means I will analyze, first of all, each column individually or each feature individually. Let me analyze that. Bivariate means 2 at the same time, like survive versus P class. Okay, survive versus sex, survive versus age, survive versus sibling, survive versus PR means 2 variables at a time. That will be your bivariate analysis. So both analysis we have to do. So first I'm going to do univariate analysis, and I'm going to check the survived column first of all. Let me check a picture. What is how many people died and how many people survived out of the entire 891 people? So I'm just plotting the SNS.count plot on the survived column. So I run that, and immediately I make an idea. Okay, 0 is very much high. That means most of the people died. And how many died? You can see the numbers from here approximately. If you want to number, you can get the numbers as well. How to get the number? That's very easy. df column is survived, okay, dot value underscore counts, and it will give me actual number, sorry, dot value underscore counts, and it will give me the numbers as well. Okay, as we can verify, 0 means 549 people died, 342 people survived. And if we can verify from here, this skill is around that one only, 549 approximately. And this is 342. So if we can match it from here, same information is almost being communicated by this column. The picture looks better. Picture looks better. Okay. Most of the people died and very few people survived. Okay. And if you can understand this way, you can further do analysis. Means if I want to plot, think this way or more smart, I want to show percentage. I want to show percentage out of the total, how much percentage people died and how much percentage people survived. You have to think that way. Okay, you have to think that way, and you can easily do that. How? I'm giving just your hint. Just tell the type of this. What is this type is? What value it is giving? Let me check it. Okay, it's a series. Remember, and series can be accessed very much like a list. Series can be accessed very much like a list. For example, I need first element. So first element is 0. Second element is 1 of the list. So I'm getting 549. Right? I'm getting 549. If I pass 1, I'll get the person who's got saved. That is 340. Okay. So this is the way actually when you will be working on, you will be thinking by yourself what I want and what is this data type? How can I access this data from that? Then easily things are there. Once you are able to access this number, you know the total number is what? 891. So you can divide this number, right, by your 891 and you will get your desired result. Am I correct? Right? So I can divide this by 890. I can do first of all multiplication example by 100 and divide it by 891 total people. And let me execute it. Okay, I get 38.38% people survived. That means how many died? Approximately 62% people died. And nobody is going to tell you these things. You have to think on your own from the existing data, what information I can extract. Okay. And I didn't even plan to tell you this thing, but immediately it came to my mind. Okay, this is a good insight that we can extract. How much percentage of the people died, and instead of seeing the number, percentage makes a good sense. So 38% people died and people survived and 62% people died. Okay, I seriously didn't plan this, but immediately looking at the data, it came to my mind, okay, we can think this way also. So I'm deleting this again, moving back. Now I'm moving to, same thing is here, value underscore counts, perfectly fine. Now I'm trying to check the passenger class structure. Okay, passenger class structure. How many people are in passenger class 1, 2, and 3? Let me check it. So I came across most of the people are from passenger class 3. The minimum are in the passenger class 2. Later on, we will also check which class people died more. Okay, that will be bivariate. So we have to do survived versus P class. Only then we will be able to do that. Similarly, let me check how many people are male and female. So again, doing the count plot on the same. Okay, so males were very much high, females were less in numbers. Around 580 something was male and around 300 were female. What data is saying. Similarly, sibling and spouse, I can check it. So there were several people who were having 0 siblings, and correspondingly you can see the structure. Similarly, parent and children's structure, several people are there. Most of the people are those which are not having any parent children. Embarked means where they boarded from. Where they boarded from. So let me run that. And most of the people boarded from this S. S has a, I think, Southampton, if I'm correct. If I'm correct, S stands for Southampton. So most of the people boarded from Southampton. These are insights of the data that you have to see before building your machine learning model. What I'm trying to learn, okay, at least somebody talks to you where the people, most of the people on the Titanic were traveling from boarded from Southampton. Something like that structure. Okay. Now, all the categorical column, all those columns which I've seen, now there is some continuous variable outputs. Which one those? age and fair. Okay, age and fair are there. Let me check a distribution of them. They are numerical columns, so no me of doing the count plot on them. They are continuously continuous output. 26, 23, 24. Here we have limited data point. 3, 1, 2, right? Sibling 1 to 10 maximum. Parent children 0 to 10 maximum, something like that. And those, your floating point output 22.0, 38.0, something like that. What you have to do, you have to check their distribution. How is their distribution? And distribution, we check with the help of histogram. So I am going here and trying to check the distribution plot, which is nothing but histogram of age. Okay, so I'm running this. I've got an idea that most of the people here are centered around the age of mean age, or we can say mean age of the people were around 25 or something. Okay, we have the people around the 80 age as well, around lesser age as well, but most of the age was around 25, 26. Same with the fair. Okay, this structure is you can see what is the structure. Very few people paid very high. Most of the people paid around between 0 to around 50. Okay, and most paid like this. You can see that. So you get a distribution. Now come to all the univariate analysis have been done. Now let us move to your bivariate analysis. So I'm checking now. Please tell me, as per sex, as per just survived, we checked here. Survived, we checked in the very first plot. Maximum people died and very few people survived. Let me check out of these died and survived, how many were male and how many were female. Okay, how many were male and how many were female among these survived and died and survived columns. So I have to just use the same function, sns.countplot df survived, just one extra term, hue. And in hue, you put your categorical column. Okay, you put your categorical column. So I'm coming here, which can categorize everything. And I just mentioned hue is equal to sex. Hue is equal to sex. Okay, means plot the count of survived, perfectly fine. Survived column, just make it clear about the sex. So means instead of seeing only 2 plots, you will be seeing now 4 plots within the same, but close to each other. See, is like this, like this. So where blue indicates your male and orange indicates your female. So immediately looking here, I can say that, okay, male died, female both died. Okay, but male's percentage was very much higher. Female percentage, male number were very much higher. Of course, the male were large in number, that is obvious. And female number was lesser. But in the survived column, can you see the structure? Most of the females survived. Most of the females survived. Okay, but several male couldn't survive. Several male couldn't survive. Okay. Similarly, let us check same. Let us check what was the condition. What was the condition of now survive was my categorical column. I want to see categorical column versus numeric column. Okay, means I want to know among the survived, means among the survived and not survived, what was their mean age? What was the mean age of the people who survived and what was the mean age of the people who didn't survive? So I just use the bar plot now. I just use the bar plot now. It will give you relationship between one categorical variable and one numeric variable. Okay, so one categorical, one numerical. So I just run that and get an idea. The mean age of the people who didn't survive was around 30, and a little bit lower on the those people who didn't sorry, this was the case, people who didn't survive are approximately 30, and the people who survived were little bit lesser, but not clear-cut information I can get from that. These are very close. If it is 27, 28, it is 30. So we cannot make any conclusion on the basis of age here, at least. Okay, so we get an idea. Similarly, I go to the survived, and this time, I'm gonna check. Okay, check one thing in the survived. Check which passenger class people survived more and which passenger class people died more. So again, I'm doing the count plot on survived. And U1 passenger class, there were only 3 classes. So again, it is a categorical column. So only 3 classes are there. So I want to separate them. So I want to plot again survived column, which will be showing the count of survived versus unsurvived. But again, divided in terms of passenger class now. Okay, there were 3 classes, and now an interesting picture is coming. See, among the died people, who died more? See, can you guess it? Who died more? The passenger class 3, who are having the lowest fare, who are paying the lowest fare. Unfortunately, those people died more. And who died the least? Who paid the highest amount of fare. You can verify from here. And same thing you can verify from here. The person who paid the highest was the survivors. Most of them survivors. Okay, so one strong conclusion we can make means it has a strong influence on survived column. If a person is belong to the class 3, that means his chances of dying are much more. Very strong in case of Titanic, because I think that was below, very much near to the base of the ship. So water entered from that place actually. That's why they didn't get the time to survive. That was the only reason. This was not the monetary issue. Actually, water came from bottom inside, and those cabins were not even the cabins. They were very much like a chambers only for the passenger class 3 people. So water inside, and they didn't get the chance to survive. So we can easily see that from the picture. These are the insights that whatever we are doing, these are EDAs, exploratory data analysis. Okay. Same now, what we are trying to do, we can do plot again, survived versus age. You want to see mean age of the people who survived and not survived. But this time, further I want to categorize, means I want to see age versus survived. Perfectly fine, I will get the mean age. But this time I want to see further. Okay, mean age is fine, but differentiate that mean age between male and female. So I put one categorical column with the help known as hue is equal to sex. Okay, whenever you see extra insights, want to see extra insights of a categorical column, just enter with the term hue, very much like we did earlier. So I'm running it. I'm getting a data. Okay, this is what earlier we would have seen only 2 things: mean age of the survived, mean age of the not survived. Now it is telling me mean age among the, this is what, this is the, those people who died. So mean age was around 33, 34 of those who died. And in the females, that was around 25. Okay. But in case of those who survived, for the males, that age was around 27. And for female, little bit on higher side. Okay. Little bit on higher side. So small conclusion I can make. If the person has died and his age is around, if a person is around 30 plus, how much age is that? 32, 33. His chances of dying is more. And female is having more age, his chances of survival is a bit higher side. Okay. Next, same way, what we are trying to plot, bar plot between DF side and survived and sibling and spouse. Same way, trying to find out. Not very much information I'm getting among the side survived or not, because this is the sibling is having very small numbers. If you go to the SIB-SP plot, where is the SIB-SP plot? Let's see, most of the people are having 0. That's why you are seeing the number between 0 and 1 only here. So not much information is being communicated to us by this. So you can move ahead. Now check between survived and embarked, when where they boarded from. So I am doing the count plot between survived, but categorized by embarked, where they boarded from. Okay. So I run this. Okay, perfect. So most of the people died. Those people died were embarked from S place, Southampton. Similarly, those people who died or even got saved were from Southampton, because we earlier saw most of the people boarded from Southampton only. We saw that, if I'm correct. See, most of the people boarded from Southampton only, means nearly 700 or 650 people boarded. So of course, their dying chances are more because there are a lot more number of people. So most of the ratio they will maintain only. Same picture is being communicated, nothing special information we are getting, because see the ratio. Mostly are from Southampton, then C, then Q. Okay, so it is decreasing, and I think the same picture we are getting here. So not much information we are getting from this data. Okay. Now there are two numeric columns, floating point columns, age and fair. Let me check what is the age and fair relationship as hue by the survived. So I will see differentiating that. Let's see what information I'm getting. So I'm getting a scatter plot. 1 means survived, 0 means not survived. So we can create a picture. This is age, this is versus fair. So we can see our age is spread. Age is spread. We are having every age person, and fair normally sticking to this person. And these things, can you see, these are nothing but outliers. Okay, normal trend is not going below above this 250 fair. Nobody is going, but few people are paid there. So from a scatter plot, we can get this information. You can clearly see this information. These are nothing but my outliers. Okay, easily we can see that. We totally separate from everyone else. Totally separate from everyone else. These are our outliers that should be removed. So in the last, what you can do the pair plot. Okay, you can do further more analysis if you want, but this is a basic primary univariate analysis we did, bivariate analysis we did, and we understood something. Further more has to be done, don't worry. And we can do pair plot. If you want to see relationship between all the variables, just click on run. Again, it will do bivariate analysis automatically of all the plots. You don't have to think. It will automatically plot the graph from you. If some information you think is suitable for you, you can analyze same thing from you. It will automatically do the how to read it. I will tell you. Suppose like this. This is survived. So this entire row is for the survived. Entire row is for the survived. And this entire column is again for the survived. So intersection wise, you can see, for example, here only. So this is the graph between fair and survived. This is the graph between fair and passenger class. This is the graph between fair and age. We just saw that. This is the graph between fair and sub-speed. Same, you can see any kind of structure if you want to get, you can do that. Or if you are in very much hurry, you don't want to even waste the time, your pandas profiling is there for you. You can do the pandas profiling and it will give you the picture. Now let us see one thing. Let me plot one more thing, very important, the box plot. Okay, which tells me about the outliers as well as about my 25 percentile, 50 percentile, and the 75 percentile. That is Q1, Q2, and Q3. So all the numeric columns, box plot will be plotted here. And it will give me some idea. You can see the outliers are available here, black. These points are even above the maximum value. So these all are your outliers, which you can see here, which you can see easily here, right? Here also we have an outliers. Here we have outliers. Here we have outliers. So these outliers needs to be removed. Because rule was, remember, what was the rule? If your values are above Q3 plus 1.5 times of IQR, okay? Q3 plus 1.5 times of IPR, above that, remove those points. Similarly, Q1 minus 1.5 times of IQR, if points are below that, remove them. Those are outliers. Okay? We'll deal with that, don't worry. Now, very important thing. As we saw in this column, which column? This column. What is this age? Several missing values are there. Perfect. Okay, missing values are there. So what we need to do? We need to do imputation. And it is a floating point number. If you can see that, 22.0, 32.0, something like that. So what we need to do, normal rule is that replace your column's mean, replace your missing value by the column's mean. This is the general rule. We can do that. Certainly we can do that. Age has a missing value. But what we can do, we can replace the missing values by the mean of the floating point numbers. So we can certainly do that. But you should explore. Further. That can be done very easily. I can do that. What I can do, I can simply do this thing, df/age, okay, dot fill NA, okay, value equals to df age dot mean. Sorry, I can do that. But before doing that, explore all the options. Is it fine? You can do that. Your machine learning model will work. But try to look after, is there any other option? Some other column can give me some information, which will be right. Okay, which will be right. Okay, so suppose I replace it by this way. So let me just delete this and let me just check the mean value. What is the mean value of the age column? 29.69. Perfect. I just put it down. I put replace in the fill any. Remember it is 29.69. I'm deleting it. But before doing that, let me check, is there any relationship between passenger class and age, or any relationship between survived and age, so that I can correspondingly substitute that, or any relation between sex and age? Means males mean age is this, females mean age is this. Is there any kind of relationship something like that? If that is the case, so better, if males mean age is different than the females mean age, better you replace that way. Replace all the entries which are having male in the missing values by the mean age of the male. Similarly, for the females, replace the missing values of the female by the mean age of the female if there is big difference. So we are going to explore that, but that will always work, that I told you. Calculate the mean value of the column, substitute that. It is going to work, but your performance can be further increased, that if you explore each variable properly. So I'm going there. Okay. Let me check the relationship between sex and age. Is there some hint I may get? I may get some hint. Means males and females have a big difference in the age. If that will be the case, I will replace corresponding males mean and females mean age. So let me run that. But honestly, I couldn't find much difference. It is around 29 or something, and it is also around 29, 28 or something. So not much difference is there in the median age if you can compare. Even min and max are very much closer. Leave it. Let me go to passenger class and check it. Is there any hint I can get from the passenger class and age? May I get something? So I run it and I get some attraction now. Can you see the difference is a lot more? Here the maximum age is way high in the class 1. Here it is low. Here it is small. Even median age is having several difference here. Are you finding it right? So can we do one thing? For those missing values which belongs to class 1, we should substitute by the mean age of those people who are traveling with the class 1. Similarly, for missing values corresponding to class 2, replace them by the mean value of the class 2 only. For this one, replace them by the mean value of the class 3, meaning your work is increased. But trust me, your model performance is going to be better. So how can we calculate? One by one, we can calculate, okay, what will be the mean age of those person who are traveling in the class 1? Very easy. I will say that DF passenger class equal to 1. Okay, DF passenger class equal to 1, passing in the DF. What it will give me? It will give me only those rows which belong to class 1 of the entire data frame. From that, I extracted my age column. From that, I extracted my age column. Now I am saying, okay, fine. Now give me the mean. If you want to see, let me go above. Sorry, let me go above and let me show you first this thing. Okay. If I run this, let me show you df.head, that is better. So I'm getting only passenger class 1. Oh, I hope you can notice that. Okay. And if I put age here, I will get only and only.
अपना बॉयलर रख के गई है या छोटे लेके गई है?
वो उसका नहीं था, उसके फ्रेंड का था। आई डोंट थिंक वो रख के गई क्योंकि रस्सी तो बाहर ही है।
Okay, so I put an age here. So I am getting just age here. So after that, if I put mean, I'll get the mean of this one. So I'm running the same thing here. So I'll get the mean age of those person who are mean age of those are who belong to the class 1. Similarly, we can go further. If you want to check it before substituting anything, let me check the missing values here of the top. Let me check the top 20 rows of those person who are traveling in the class 1. I'm intentionally doing that, okay, because I want to see in age, this 31 index is having missing value. This 31 index is having missing value. Remember that. We will use that, okay? Similarly, same way I can calculate the mean age of class 2 people. right? We can calculate the mean age of the class 2 people. So I'm running that. I got it. Delete this one, it's not required. Similarly, I can get the mean age of this passenger class 3. I'm running it. Okay, I got it. So notice down everything. What we noted down for passenger class 1, the mean age is 38. I will note it somewhere. Okay, note it. For passenger class 2, the mean age is 30, in fact, 29.87. So it will be 30. For passenger class 3, it will be 25. Okay, so what I'm going to do, I'm going to create our own function now. I'm giving that function name as impute age. Now you may be learning how the complete machine learning works, right? Several things, whatever we have studied, everything is going to come into the picture now. Everything. Sometimes you will take longer, 3 days, 4 days, 5 days, 15 days to build one machine learning project. I'll finish it, don't worry. It may take even 8 o'clock. Don't rush. At least you will get an idea. Okay. So I'm creating a function def impute age where I will pass some column names. Okay. And I'm saying that I will pass such way that first column I will pass in the form of a list. So first column will be known as age and second column will be known as passenger class. And after that, I'm simply saying that if PD is null in age, means if in age column there is null value or missing values, okay, then check. If passenger class is 1, then return 38, because for class 1, if we go back, where is class 1 mean age? We calculated it is 38, right? Similarly, if the passenger class is 2, return 30. Let me make it 30. Okay. Similarly, if passenger class is 3, doesn't mean to mention the only 3 classes are there. So 1, 2 are checked. So it's obvious third class will be only class 3. Else return this 20. I created a function. As simple as that. If null value is not there, means this condition is failed, means nothing is going to happen above these, then simple, whatever age is that, return that. I created a function, this imputation function. Now what I'm going to do, I'm saying that df age equals to df. Okay, I'm taking 2 columns now. Which columns I'm taking? Age and passenger class. Why? Because this function needs 2 arguments, 2 columns, 1 age and 1 class. So same order I mentioned, age and class. Okay, age and class. Then I said dot apply. This method that we have studied, any method we can apply to every row of our data frame. In fact, right, any row of data frame, in fact, it will be, if we are accessing individual column, it will become a series only. Okay. And in that, I pass my function which I have created. Which function it is? Impute age. So I just put it impute age here. So automatically it will check this rule. For every row, it will check this because I'm applying here. So for every row, it will check this rule. That's why it will mention axis is equal to 1. Okay. For each column, each row, it is going to check this and apply. Once it is done, let me execute it first, this function. And let me execute this function. And this time, let me check 20 rows. Why I did? Because remember, in the index number 31, we were having NaN values here, remember? And 55 also NaN values. So it must have replaced by 38 because that is class 1. So let me check here. For 31, 38 is here. For 55, 38 is here. So now I have treated smartly with the missing values in the age column. Okay, I've successfully managed that. If you want to check, I can check once again. I can say simply sns.heatmap, and here I'm passing df.is null. Okay. Let me execute. Now see, we cannot see any missing value here in the age. Is it fine, everyone?
Yes, sir.
Is it okay? Right? Now there are just 2 missing values in the embark column. If you want to check it, you can check it. df dot is null dot sum. Okay. Age is gone, but embarked has only two values. The two values are very less. We can drop them. We can drop them. We can say that df dot drop any. df dot drop any. And if we go inside, let's see in place is equal to false. So let's make it in place is equal to true. Okay, I'm coming here. In place equal to just two columns, rows are there, so doesn't make much sense in that. So I'm gonna drop that. Let me run this. Okay, execute it. Let me again run this and let me check the missing values once more. Okay, no missing values anywhere. Is it fine, everyone?
Yes, sir.
Others, at least who are listening, please tell me.
Yes, sir.
Okay, great. Now, what we are going to do, there is very important parameter known as skewness. Okay, there is very important parameter known as skewness parameter. Before that, let me delete all these so that you can get a clear picture. Okay, I'm removing this. Perfect, fine. I'll check it later on. Don't worry, skewness I'll tell you later on. Okay, so let me come here and let me draw the distribution plot of everything. I'll tell you why I'm doing that and why I'm saying skewness. I'll tell you later on. Let me run this. Okay, I get distribution like this. I get some distribution. What are the, what is the distribution plot? We just count the frequency of occurrence. How many times what values are occurring. So 1 is occurring this much time, 2 is occurring this much time, 3 is occurring this much time. Means most of the passenger are having passenger class 3. Similarly, let me run on the siblings. These are discrete values. Most of the person are having 0 value. That's why it is centered around 0. See the density curve. Now come here, run it. Again, the same problem. Most of the passenger having centered around 0. These kind of graphs are known as skewed graph. I'll show you within few seconds. You will come that. Okay. And let me check the fair distribution. Okay. Most of the people are centered around here. Very few people are having very high fares here. Very few people are having very high fares here. Doesn't matter. Now, before moving further, what we can do, understand. We have a categorical column here. Which one that is? 2 columns are there. Sex and embark. Sex and embark. Both of them I can convert into numeric column by using 2 methods. Understand. One, using getDummies function that we have studied earlier. For that purpose, I have nothing to do special. I will just go here, and just choose pd.getDummies and df. It will immediately create those columns. It will immediately create those columns. Okay. But sometimes this way, what will happen? Suppose I have a column known as embarked, C, A, or S, 3 columns, perfectly fine. So I can have values. If 3 entries are there in the embark, so I will have 3 new columns generated due to the embark. Okay. And that will be one hot encoding. That will be one hot encoding, something like this. Suppose, as I told you, suppose there is a column known as sex in which people are male, female, again male and female. So new columns will be created, sex underscore M, sex underscore F. And whenever male is there, it will be 1, corresponding female will be 0. Whenever female is there, male will be 0 and female will be 1. This is known as one hot encoding. Okay. And this kind of encoding works perfectly when there is no numeric weightage between male, female, and everything. Male and female are considered equal. So for that case, it is perfectly fine. But sometimes there will be scenario where there is numeric weightage even in the category. For example, you are building a project where education matters a lot. So you are saying that education level, where somebody is PhD, somebody is master's, somebody is graduate, somebody is even intermediate, somebody is high school. And these are very important for you. Okay. Education factor is very important for you. Somebody told you, you check me. You want to check that education wise, does it impact the crime rate or not? So these are in some particular order, right? PhD comes at the top level. Then your masters come at the second level. Then graduation. Then integer. There is particular order. Similarly, when you buy products, so double XL has the largest size, right? XL has a smaller size. Your L is other size, then medium, then small. There is also some order in that. These are known as ordinal variables. Whatever we are writing are known as ordinal variables. These are what? Nominal variables. They don't have numerical weightage. For nominal variables, your dummy variables are very good. Perfectly fine. Perfectly fine. But your ordinal variables should not be treated this way. For example, double XL is largest, so it should be given maximum weightage. Suppose I'm saying smallest is 1, represented by 1. Medium will be represented by 2. Large will be 3. XL will be 4. Double XL will be 5. Similarly, PhD will be the highest. Lowest will be high school. Suppose 1. Intermediate 2. Graduate 3. Matrix 4. PhD 5. This kind of replacement you should done in case of ordinal variables, where their order is matters. Order matters. Similarly, your grades, A grade, B grade, C grade, but top grade is A grade. So it should have maximum weightage 3. It should have second maximum weightage. It should have lesser maximum weightage, something like that. For that purpose, pd.getDummies is not a good method. It's not a good method. For that purpose, what I prefer map function that we studied in Python, list especially. Okay, and if we consider individual column of a pandas, remember it considered as a series, and series behaves very much like a list. So what we can do, we can see simple what I said. I'm just giving an example. df sex, miss column, name is sex, dot map, put a bracket, and it create a dictionary and write your mapping there. Write your mapping example. I just mentioned in bracket key PhD, colon, your weightage. What is your weightage? Weightage is 5. Okay. Similarly, next key is what? Masters. So put in brackets, colon. What is his weightage? 4. Okay, like this. I'm telling dot map, inside the dot map, create a dictionary, and within dictionary write PhD, colon 5, masters, colon 4, graduate, key, colon 3. Get an idea, everyone? Please tell me how to deal with the ordinal variables.
Yes, sir.
Okay, so for that purpose, you can use your map function. I needed to tell you this. But in our case, there is nothing like that. If you see our data set, there is nothing like ordinal variables. We are male, female, and embark. Nothing special. So it is not required. But I needed to tell you how to deal with that. I'm commenting that one only. So for our case, that will work. So I'm just running it and I can check it. df.head again. All the categorical columns even should have been converted into the numeric. So perfectly now we can use them. Even you can drop these one of columns. Even you can drop this sex female and sex male. Why? You can understand. See, both are communicating same information if you check it. Right or wrong? When it is 0, that means what? She's not female. That means we have 2 genders only, right? We have only 2 genders. So person is not female. That means he's what? She's what? Male, right or wrong? So both columns are communicating same information. So you can drop one column. You can drop one column because both are communicating same information. Similarly here, we have 3 columns. Out of the 3 columns, you can drop one column. You can drop one column. Why? You may be asking, sir, why we can drop one column? Because in case, if this is 0, this is 1, perfect. This is S. In this case, when both are 0, that means neither it is Q, neither it is S. It is something else. And what is something else is C. So when you are using dummy variables, whenever you are using dummy variables, you can always drop your one column. You can always drop your one column. I hope you're satisfied with the argument. Tell me everyone, is it okay?
Yes, sir.
Okay, logic is clear, perfectly fine. Okay, so we can check this thing we have done. I think this numeric columns also we have plotted. Let me plot it once more, no issue. What happened? Under Cox, what error is it showing now? Layout to 2:2 doesn't require size. What we are doing? Okay, actually thing is that we have increased the columns. That's why the only issue is happening. We can increase the layout. Suppose it will increase 4 into 3. Now it will show me. Yeah. We'll get different box plots. And in the box plots, we can see immediately our outliers are available. And okay. And remember, you should be able to troubleshoot the problems, read the errors and understand. Now we are time to remove the outliers. Simple. Now it's time to remove the outliers. So there are different ways to remove the outliers. One way to remove the outlier is just remove those points which are above Q3 plus 1.5 times IQR. IQR is what? Q3 minus Q1. Okay. Similarly, remove those points which are less than Q1 minus 1.5 times IQR. Okay, this is one way. One way is that remove those points whose Z value is greater than 3. You'll be talking, what is this Z? The Z is nothing but xi minus mu by sigma. What is mu? Mu is your mean of the column. Sigma is a standard deviation of the column. Okay, and xi is a corresponding value of each row of the column. Suppose I'm having value 1, 2, 3, 4. We'll put 1 by 1 value here, 1 by 1 value here, 1 by 1 value here. Mu will be the property of entire column. This thing we have studied, and sigma will be the property of entire column. So this will be calculated only once. You will only substitute 1, 2, and 3, and this will give you the value of Z. And those entries you can remove whose values are greater than 3. You may be asking, sir, what is this Z? Why it signifies? Actually, let me show you. Let me show you one thing, very important thing. Z value. Okay, let me bring it down and let me type Google Z value in statistics. Fine, perfectly fine. I want to show you a graph actually. By that you will understand everything. This is Z, x minus mu by sigma, perfectly fine. Yeah, this is the one I want to show you. Okay. If your values are normally distributed, and it is good to have your values normally distributed, that's why we will use the skew term. We will deal with the skew term. You will see that if your values are normally distributed, then what should be happening is that your maximum value, see, if this is the mean, if center is the mean, then one standard deviation away here, one standard deviation away here, means if we consider this, it consists of 68.27% values. 68.27% of your values. 2 standard deviation away, you are having 95.45% of the values. And 3 standard deviations, you can see mu minus 3 sigma. Can you see that? This is mu minus sigma, mu minus sigma. So one standard deviation away here and there consists of 68.27% values. Of all the values, your 68.27% values lies within the one standard deviation away left, one standard deviation away to the right. 2 standard deviation away, mu minus 2, mu minus 2. Of entire values to be 95.45%. And if we move 3 standard deviation away each side, then it consists of 99.73% of your data, right? So most of your data will be available within the 3 standard deviation away. So any values which are greater than this means it is not coming into 99.73%, means it is not following our trend. It is above than 99.73% people think. So those persons are considered as outliers. Same way we are considering. So those Z who are values are 3 standard deviation away, then that will be considered as outliers. Are you satisfied with the argument? Please tell me, please.
Yes, sir.
Is it fine, everyone? Most of those values will be considered only 3 standard deviation away from the mean. Okay. For the same purpose, we used a library known as SciPy. From that, we have imported a module stats, and from that, we have imported a function z-score. Okay, imported a function z-score. No issue, you can write it down somewhere. It's almost impossible to remember everything, but create one project and keep your one project file ready with you. Whenever you need it, open that project, copy it, and use it. At least you know that how it is working under the hood. Okay, so z-score. Now, this will be give me the absolute value. Absolute value means no signs and everything. I just need that thing. I just need everything because sometimes it will be positive, sometimes it will be negative. So I just need absolute values of that, means mod of that. So this function z-score of df will calculate me the z-score of entire data frame for every point. Okay. Now I am saying, give me only those rows. See, df.log function is here where z-axis is less than 3. Okay, so give me all those rows and columns where the z-score is less than 3, means 99.73% of data. And after that, we are showing, okay, original shape was df.shape. And after considering this, removing the outlier, shape will be dfx.shape. So I'm running this. Okay, the original data was 889 rows because earlier it was 880, 891. Remember, MBACT has 2 missing values. So we dropped them. After dropping them, it became 889. And after which, see how many outliers were there. So after removing the outliers, we get 747. I hope it is fine.
Yes, sir.
Okay, so this is now outliers have been removed. Okay, now what we are going to do, we're going to separate our X and Y. So I need everything in the X except survived column, and survived column should be my Y. I run that. Now let me check my head, top 5 rows of the X. See, it doesn't have survived column. Let me check my Y. Sorry, Y. So I get this. Okay. And let me check the skewness of my data. Just a second. Entire data frame skewness. Skewness means how your data is distributed. Normally, it should have a perfect normal distribution, something like this. Something like this. Means it is mean. So at mean, you have a maximum value, and it is symmetrically distributed to the left and right. To both the side, you are distributing uniformly. Here and here, both the side uniformly. But if it is something like this, okay, so most of the values are considered here and few values are here. This is known as positively skewed data. Okay, and similarly, if you're getting something like this, it is known as negatively skewed data. Okay, and skewness affects your performance. It should be normal distribution. And luckily, we have things, if your data is skewed, skewness will be there, but up to 0.55 is allowed. Up to 0.55, skewness is permitted. It's fine. It won't affect much performance. But we can even convert this positive skewness, reduce this positive skewness, reduce this negative skewness by transformation. Example, log transformation, power transformation. This will help us in reducing the skewness. To deal with the skewness, positive or negative, we have to use transformations. Transformation, okay? And transformations, which kind of transformation? Mostly log will do. If log is not working, your power will do. Power, square, cube root, and something like that. Let me show you that. Okay. So we are going to check our skewness in the data. This is, I think, last thing we require to do. So I just clicked, see, it is 0.48 in the survived, even it is a categorical, sorry, it is our output, so don't leave it. See, the passenger class is having 0.63, age is 0.51, acceptable, sibling is 3.691. I don't think so it is going to be affected because it is having only discrete values. P-arc is 2.74. Main important thing is this one. This one. This is continuous output, 4.80. It should not be above 0.55. See? Sex female 0.62, female minus 0.62, embark this, and everything. 2 numeric columns, one is already satisfied. And sorry, 2 continuous output column, age very much satisfied. And this fare is not satisfied. So what I'm going to do, see, as simple as that. I'm saying that I've separated X and Y. So I'm going to remove skewness in the X. I'm going to check in every column of X. I'm saying for column in X dot columns, if X dot skew, X dot Q at location of corresponding column is greater than 0.55, then in that particular column, do one thing. What you need to do, take the log of that. Take the log of that. Log will do the transformation and it will try to reduce its skewness. So I will run this cell. Okay. Similarly, to remove the negative skewness, I'm using square column. Okay. So in this case, negative 0.55 is considered. I'm saying for column in X dot columns, if X dot skew at the location of column is less than minus 0.55, okay, minus less than minus 0.55, then take the power that is square. Both can remove the skewness. So I'm running that. And now let me check the skewness. Okay. So remember our fair skewness was 4.80. Okay. And let me check what happened with that. Now skewness has come to 0.40. It has come to 0.40. We needed 0.55. It is bringed even lesser than that. Okay, so some columns will be reduced, some column will not be reduced for sure. Don't worry about that thing if it is not going to be reduced, but they are reduced. See, sibling was 3.69. Now check it. It has come to 1.65, at least reduced. If not come even 0.55, it has at least reduced. Okay. Similarly, P arc, if you see here, was 2.74. Now it is reduced at least. Okay. Negative, it was minus 0.62. See, something has happened. No, it has not happened. Perfect. No issue. Okay. So at least we are able to reduce some of the columns, which has been done. Now, very simple. Last thing we have come.
Sir.
Yes, yes.
Sir, here, why you are taking 0.5 means 55 only?
Actually, it is a standard normally people follow.
Okay, sir.
Standard
then it is
normally.
fine.
Yes, it is a standard. Okay. If you can further reduce, that will be very good. Normally, it is saying that it is accepted. 0.55 means that it is a standard normally people follow. Okay. Or more lesser you can do, you can try one. Okay. So now, again, now we are coming to the last part. We have checked the skewness, remove outliers, do all the EDA. Remember, then what we do? Train, test, split, and standard scaling. Scaling is required, remember, so that your high numerical weightage doesn't affect the performance. So I'm doing that, running that, splitting my X and Y. Okay, same way we have done earlier. Fitting and transforming my training data and transforming my test data on the scalar. And this time, for example, I've taken a random forest classifier. I've taken a random forest classifier from Ansible. You could use anyone, doesn't matter, any algorithm you can use. So I'm running it. I'm intentionally using it so that you can learn that. Okay. Creating an instance of that, random state 1 is specified. I'm fitting on the training data. Okay. Now I'm importing some matrices as we did earlier, checking the accuracy on training data. Okay. Checking the accuracy on the training data. Very good. 98.59% accuracy we are getting. Let's check on the test data. I think 79.21% accuracy. Rest things, I think I'll cover one more day. Okay. And whatever is remaining, I'll cover that thing. Is it fine, everyone? Hope you get in some insight from how to work on a machine learning project.
Yes, sir. It is very informative, sir. Means
yes.
Total package.
Yes, it was very much important. It was very much important.
Sir, another thing, you should share this.
Yeah, I'll share this file.
So that actually, sir, we can definitely practice it, and we will keep it aside, and we will practice it, and that will be better.
Sure. I'll do that. Don't worry.
Okay.
Thanks, everyone. I'll take one more session, beta. I'll inform you. I'll take one more session, and whatever things are remaining right now. For example, even we can improve this accuracy. Because our data set was imbalanced. We will try to make it balanced as well. Okay. So one more day I will take. Okay. And one more project we'll work on, or at least we can remove the drawback of these. So you can get accustomed how to work on those. Okay. So thanks, everyone. Thanks for your time.
Thank you, sir. Good night.
Good night, Beta.